Hi, Joe.
Hello.
Joe, I can always count on you to make sure that I sent out the right message.
Yeah. I'm just sitting here waiting, freezing,
Yeah. You're freezing? Come on, it's
It's
not even that cold out there.
And it's freezing in my room.
As your mother would say, put a sweatshirt on.
Yeah. To have comforter on. I have like a giant blanket on right now.
Hi, Jessica. How you doing? Jessica. She's being shy right now.
I'll be here, but I'm gonna be right back.
No problem, Joe. Jessica.
Hi, how are you?
I'm doing fine. Did you get my message earlier?
Yes, thank you so much.
No, to be honest with you, Jessica, you guys were always going to get all the participation points.
Okay.
I was really, I don't know if you appreciated it or not, but I was really.
I most definitely did.
The only way I'm going to get you to get involved in that is if I make some sort of penalty for your not doing it. And literally,
Makes sense.
Jessica, I've seen so much good work come out of there. I can't even tell you how much good conversation that has come out of that discussion forum. It's probably the most valuable thing of everything that I've put in. Did you answer the last pop quiz?
Yes.
So,
no, sorry, not the very last one. I haven't done that yet.
all right.
The second one.
It's not a big deal. It's just, there are certain things I did for this online class that I don't normally do. And as a consequence, I wanted to get a feedback on whether they were successful or not.
Okay.
Okay. That's basically all that is it's a survey. You're going to get 10 points for that. If you don't even have to answer the questions. All you're going to do is, at least to the first one, put in no answers or no response.
Okay. Yeah, I'm going to do that.
Whatever. I won't look at the answers until a week after I post grades in the lecture. Okay.
Okay. Sounds fair.
How you doing with this stuff? Does it seem okay?
Yeah, I think okay with it. I still need to look at it more. I was just trying to catch up on the last homework assignments.
I understand. Perfectly understand. You know, the last homework is going to be extra credit.
Yes.
Okay. Okay. Joe, you back?
Yeah, I'm back.
All right. Doesn't seem like we're going to have a whole lot of other people here, but it seems a shame for the last one. But hey, things happen. I'm going to begin with this slide. And basically, this gives a summation of everything I talked about last period. There are 4 intermolecular forces you need to deal with: dispersion, dipole-dipole, hydrogen bonding, and ion dipole. They increase in strength going down this chart. Ion dipole are the strongest, dispersion are the weakest. Now, a couple things you need to remember about dispersion. All molecules have them. Even dipole-dipole, hydrogen bonding, and ion dipole, they all have dispersion as well as those other intermolecular forces. A couple things about dispersion. The bigger the molecule, or the bigger the atom, the more electron density it has. The more electron density it has, therefore, it is going to have a stronger intermolecular force. And another thing you need to understand is, the stronger the intermolecular force, the more energy required to boil it or to freeze it. Now, when we go into dipole, the difference between dispersion and dipole. Dispersion involves electrons that are temporarily on one side of the molecule or the other. So that the electrons that are on one side could just as easily flip to the other side like that. When you have a dipole, it's a permanent charge distribution. Okay, so that's the difference between dipole and dispersion. Hydrogen bonding is a special dipole. Hydrogen bonding involves molecules with hydrogen bonded to fluorine, oxygen, and nitrogen. Only instance in which you can have hydrogen bonded. They're bonded with fluorine, oxygen, or nitrogen. If you have sulfur with the hydrogen there, that is not a hydrogen bond. That's a dipole. Hydrogen bonds, because of the electronegative differences between fluorine, oxygen, and nitrogen and hydrogen, make those charges even stronger. If the charges are stronger, the force, the intermolecular force, is stronger. So that if I was comparing something like H2S and H2O, H2S does not have hydrogen bonds. It only has dipole. H2O has hydrogen bonds. So therefore, H2O has the stronger bonds. H2O is going to boil at a higher temperature. Does that basically make sense to you? I need an amen every now and again, guys. Is that making sense to you?
Makes sense to me.
All right. So what we're doing right now is we're going to go on to boiling and discuss what's really happening in boiling. I don't have a life, so I get to watch water boil. And if you ever do watch water boil, what you see is you see those little tiny bubbles. When you just heat up the water and you see those little tiny bubbles, you start to get excited saying, it's not going to be much longer. My water is going to be boiling in the next second or so. What those little tiny bubbles are the gases that are dissolved in the water. They get gone first. Then what happens is you get the gas starting to form a bubble. It starts to go up, it bursts. Next time it gets up a little higher, bursts again. It's only when that bubble gets to the very surface and the molecules start to go into the air that we're at boiling. Now, there are some factors which influence the rate of vaporization. Do you have any idea what those might be? Any idea? It'll come to you guys.
Forces.
Very good. The stronger the intermolecular forces, it's going to take more energy to vaporize that particular liquid. So if I have hydrogen bonds, those are going to have strong intermolecular forces. It's going to take a higher temperature. Now, what else may influence the rate of vaporization? Do you think Florida has more water vapor in it than Manitoba? What could be the difference between the climate of Florida and the climate of Manitoba?
I don't know what Manitoba is.
Canada.
Okay. One's going to be hotter.
Oh, so do you think, Joe, do you think we're going to have more humidity in Florida, or do you think Canada is going to have more humidity?
Florida.
So the amount of energy we put into this is going to influence the rate of vaporization. The last thing is something you may not think of. If I have the surface of my liquid about how big my watch face is, and I have a cup. Which one do you think is going to boil faster?
You're right.
Okay, let me ask you another question. If you have water in a pan as opposed to water in a pot and you're heating them up, which one will boil faster?
The pan.
The pan, because the surface area is bigger. That also affects the rate of vaporization. So if we're looking at temperature, what happens is, in order for something to get into the air, it has to have enough thermal energy to escape where it is. If I'm at a low temperature, I'm going to have a certain amount of molecules that have that much energy. If I increase the temperature, what that does to the curve is it makes it wider and flatter and smaller. The effect of that is that I now have more molecules with the minimum kinetic energy needed to escape. So higher temperatures are going to lead to more vaporization. Now we have to talk about that. This is a process. It's involving energy. So there is a certain amount of enthalpy or a certain amount of energy that's needed to put into the liquid to make it vaporize. Specifically, by definition, the heat needed or the energy needed to vaporize a mole of the liquid to a gas is called the heat of vaporization. And basically what that is that's the energy needed to overcome the intermolecular forces that make the substance a liquid. And is it making sense to you guys?
Yes.
All right. We got a couple problems here. Heat of vaporization of ethanol is 38.6 kilojoules per mole. How much energy is it going to take to completely turn 55.6 grams of ethanol from a liquid into a gas? Do I have a suggestion as to what I'm going to have to do first?
I know this one, I think.
Go for it.
And take the 55.6 grams of ethanol and divide it by the molar mass of ethanol, and then multiply it by the kilojoules, and I'll give you an answer.
Jessica, does that seem to make sense to you?
Yes. Get the moles and then multiply it by the
Heat of vaporization.
kilojoules. Yeah.
Okay, so that's simply what I did here. All I did was take my 55.6, divided it by 46.07, the molar mass of ethanol. I got 1.21 moles. I then multiplied that by the kilojoules per mole. That gave me the heat needed to evaporate all of that liquid into a gas. Okay, I'm going to need to do this one with a slideshow. Well, I'm sorry, 1 second. Yeah. If I just do it like that. All right. I got another problem here. If I apply 26 kilojoules of energy to 43.7 grams of ice, would I have any ice left? Heat is 6.02 kilojoules per mole. Do we have any idea how we're going to do this problem?
Start by finding the moles.
Okay, we can do that. We can do that. If we ice, the molecular weight of water is 18.02. So I have 2.43 moles of ice. What am I going to do now? I have two ways I can do this problem. Anything, Joe, Jessica, Min, anything that could help me here. By the way, hello, man.
Take the 26 kilojoules and divide it by the heat, 6.02.
Dynamite. Absolutely dynamite. If I take my 26 kilojoules and divide it by the 6.02 kilojoules per mole, that will tell me how many moles of ice this 26 kilojoules can melt. So if I do that, this means 26 kilojoules can melt 4.31 moles. Do I have enough energy to melt 2.43?
Yes.
You got that, Joe? Min?
Yeah, I got it.
There's another way to do the problem. I could take my 6.02 kilojoules per mole and multiply it by my moles of water. By that instance, this means if I have 2.43 moles of water, it's going to take 14.6 kilojoules of energy to do that. Did I have it?
Yes.
So if I had it, then that answers that question. Just a couple of problems you can use to work around. Okay. I have NH3 and SbH3. From what I did, if you remember about the that one slide I had with the intermolecular forces, which one would you expect to have a higher heat of vaporization? Would you expect NH3 to be higher or SbH3? Think about it logically. What intermolecular forces does NH3 have? What's the strongest one?
And typo.
Ah, but Joe, is there an H attached to an N?
Yeah.
What type of forces are those? H attached to fluorine, oxygen, or nitrogen leads to what type of intermolecular force?
Hydrogen.
Hydrogen bonding. Absolutely. Is H in this one attached to nitrogen, fluorine, or oxygen?
No.
So when I'm dealing with SbH3, I only have dipole-dipole. This one has hydrogen bonding. Now what's stronger, hydrogen bonding or dipole-dipole?
Typo.
Nope, other way around, Joe.
Man, why do I keep thinking that's? I thought that was the strongest one, but
No,
then it's the hydrogen one.
no,
Yeah.
Joe, what you're thinking of is ion dipole.
Oh, so that's
Ion dipole is stronger than hydrogen bonds, which are stronger than dipole-dipole. This one only has a dipole-dipole. Okay? Because
so
you
it'd
have
be
to
hydrogen
understand,
then.
I'm attaching SbH3 to another SbH3 molecule. That's how I'm determining heat of vaporization. Because remember, in order to get this to gases, I have to break the intermolecular force, which attracts one SbH3 to another one. So these are just dipole-dipoles between one another. In the case of ammonia, I have hydrogen bonding, which makes that bond even stronger. So ammonia is not going to have it's going to have a higher heat of vaporization than SbH3. Guys, this is what Chem 2 is all about. I start my Chem 2 lecture with this chapter. It's all about logic and being able to logically work your way through word problems like this. Okay. I'm going to stop this for a second. Stop share. And I'm going to go to the whiteboard. Okay, I have several molecules. I have water. That's an O. Pretend it's an O. I have ethanol. Those are H's around the C's. Now, you have to understand that the electromagnetic or the electronegativity of hydrogen is about the same thing as carbon. So literally speaking, all these carbon hydrogen things are nonpolar bonds, which means it is increasing. Every time I put a carbon and a hydrogen out there, I increase the dispersion character of the molecule. My next one is going to be acetone. Now, while I'm drawing acetone, I want you to be thinking. Look at water. What is the strongest intermolecular force that water is associated with? That is acetone. And I'm going to draw dimethyl ether over here in a second. All right, guys, for water, what is the strongest intermolecular force that's involved there? Come on, guys. I need you to come up with answers here. Is hydrogen bonded to a?
Oh, it's hydrogen bonding.
Thank you so much, Jessica. So, are hydrogen bonds pretty strong, Jessica?
Yes, it's the third one.
Okay. Now, hydrogen bonds are pretty strong. Now, does this have hydrogen bonds in it?
No.
Do I have a hydrogen bonded to an oxygen?
Yes, I mean, yes.
So that also has hydrogen bonds in it. But it also has some non-polar character to it. So the hydrogen bond is somewhat diluted. Okay? So this one, all hydrogen bonding. This one has hydrogen bonding with an area of dispersion. Which one do you think is stronger?
The H2O.
H2O is stronger than this one. Okay, now, do I have any hydrogen bonds in acetone? Do I have any place where hydrogen is bonded to a oxygen, nitrogen, or fluorine?
No.
And yet, I still have an electronegative difference here. So I do have a dipole-dipole bond. here. Now, are dipole-dipole stronger or weaker than hydrogen bonds?
Weaker.
All right.
Yeah.
Now, is this molecule polar at all? Is it symmetrical?
Yes.
Yeah, absolutely. It's symmetrical. So it is non-polar. The only thing this has is dispersion. So if I'm rating them from the highest boiling point to the lowest, 1, 2, 3, 4. Now I'm going to draw one more molecule out here. And that is going to be butanol. And I'm doing this to illustrate another point. Does this one have any hydrogen bonding to it?
Yes.
Yeah.
All right. But it also has this big, huge area of dispersion. Okay. Now, when we're dealing with these two molecules and trying to compare boiling points, we have a kind of a bit of a tough time, because even though this has a larger polar, non-polar character to it, it's also the larger molecule. So in effect, because it's the larger molecule, this one is going to boil at a lower temperature than this one is. Does that make sense to you?
Yes.
Okay. I'm going to stop share and go back to the slideshow presentation. And just like we predicted with those drawings, water has the highest. This one said rubbing alcohol, same basic difference. They both have hydrogen bonds. This one has a little bit of a dispersion, so it's going to be a little lower than the other one. Acetone, because it has only dipole, is lower, and diethyl, because it only has dispersion, is even lower than that. All right, if you leave a container open to the air, this is why I'm constantly filling up dog dishes. If I leave water open to the air, eventually it's all going to evaporate away, isn't it?
Yes.
So what happens when I put a lid on that? Well, at first, there's no liquid evaporated into the airspace. So what happens is, basically, I get movement in one direction. All the molecules want to get, not all of them, but there is a rate of evaporation that exceeds the rate of condensation. In other words, the molecules want to get in the air, but there are no molecules in the air to condense. As we get more and more molecules up in the air in the airspace above the liquid, we begin to have some of those molecules condense back into the liquid while we have others evaporating away. When we get to a sufficient concentration above the liquid, we have what's called a dynamic equilibrium. You have to understand the concentrations aren't changing of the concentration of the molecule in the air above the liquid and the concentration of the liquid. That's not changing. But what is happening is we're getting the molecules to evaporate at the same rate that other molecules are condensing. So even though it may look like nothing is happening, we're getting this constant cycle. Evaporation rate is the same as the condensation rate. If you can see that bunch of arrows. So at first, we have a steady rate of evaporation, but we don't have anything in the air. So because we don't have anything in the air, the condensation rate is fairly low. As we get more and more molecules in the air, we get more and more condensation. The rate is increasing, and the rate will increase until we reach a point where the rate of condensation equals the rate of evaporation. It's at that point that we have a dynamic equilibrium. And this is going to be important. You're going to have an entire chapter in Chem 2 on equilibriums. And again, I've explained these two slides then. Now, if I disturb that, I have a system. I've got the evaporation and the condensation rates equal. If I do something to disturb that, then my reaction rates are going to change to get it back to that equilibrium. To give you an example of what's happening, I have a dynamic equilibrium. If I increase that volume, then my concentration of molecules in the airspace has gone down. I need to get that concentration back up again. So what happens is I get more evaporation than condensation. The rate of evaporation increases to the rate of condensation until I get the concentration up there equal to what it was before. By the same token, if I take that space and I crush it down, my molecules in the air are now too concentrated. So my rate of condensation increases compared to my rate of evaporation until I get back to that right concentration above the airspace. When that happens, I reach the dynamic equilibrium again. So, are you okay with equilibriums and what's happening with that? Are we good, guys?
Yes.
All right. Now, the vapor pressure, the pressure of the liquid above the pressure of the molecules in this airspace above the liquid, that pressure is dependent upon the intermolecular forces and the temperature. Okay? If you have a stronger intermolecular force, it's going to take more energy to get the same amount into the air above. For example, if I have water at 200 torr pressure, I have to get that temperature somewhere around 70 degrees. Are you seeing that, guys? On the other hand, if I have diethyl ether doesn't have hydrogen bonds. Its intermolecular forces are weaker. So in order to get it to a vapor pressure of 200, I only have to raise the temperature to 0 degrees centigrade. All right, let's look at the effect of temperature on the individual substances. As I increase the temperature, my vapor pressure increases because I'm adding more energy to my system. And the more energy I'm adding to my system, I am getting more of those molecules that have the kinetic energy to escape the liquid phase. That brings us to something called the Claussius Clappeyon equation. Now, the nonlinear relationship between vapor pressure and temperature. If I look at these graphs, what's a linear equation look like? If I'm graphing a linear equation, what's it look like?
A line.
A straight line. Are these straight lines, Joe?
No.
So that means they're not linear relationships, are they? So pressure and temperature are not a linear relationship. What you're going to find in Chem 2 when you get there is that chemists all the time want linear relationships because we can relate something we can't measure to two things that we can measure. So we want to get linear relationships. We do that in the Clausius-Clappeyon equation by taking the log of the pressure and relating that to 1 over the temperature. If I take the log of the vapor pressure, that's going to be equal to negative the heat of evaporation, negative the heat of vaporization divided by R times 1 over T plus the ln of B. The beta is going to depend, it's a constant that depends upon the type of gas. T is the temperature. P of vaporization is the vaporization pressure. Delta H vap is the heat of vaporization. And R is the same constant that we've been dealing with in the gas laws. But you notice the number is different. The number is different because the label of R is different. When R was 0.08206, the label was liter atmospheres per degree Kelvin mole. Now the label of R is joules per mole times Kelvin. Different label, different number. Now I'm looking at this equation. Can you see where if I make my y ln of p and I make my x 1 over t, that I have y is equal to, this value is going to be m, this is going to be x plus my y-intercept. Can you see that? Are you seeing that this is the equation of a line? I can outwait you guys. If you're not seeing it, don't tell me yes. Are you seeing it, Joe?
Yeah, because the NB is like the constant in this equation, and the X is going to be your 1 over T, because we did this in the lab, remember?
Exactly. Perfect. Absolutely. That's what I'm talking about right now, is what we did in the lab. Jessica, are you understanding this?
Yes.
Men. Men? Okay. So, can you see if I plot the ln of P, if I have a number of pressures and I plot the ln of P with 1 over its subsequent temperature, I am going to get a straight line, and that straight line is going to give me a slope, and that slope is going to be equal to negative delta H vape over R. An example, the slope is, the line is always going to look like this. The line will always have a negative slope. So my equation of my line is y is equal to negative 4288 times x plus 18.806. If I give you this, can you tell me what delta H is? Give me a way to determine what delta H is. Jessica, what's M equal to? If I'm using, Jessica, if I'm using ln of P is my Y and 1 over T is my X, what's my M?
The negative delta H vap over R.
So that's equal to 4288. In order to solve for my delta H vap, all I have to do is take my slope value, multiply it by my R value, and -1, because this is going to be a negative number. I want to get positive delta H vap, so I'm multiplying by -R. I do that in this instance. I get my slope times my R value, negative R value. This gives me 35,650 joules. Heats of vaporization are generally done in kilojoules. So that would actually be 35.6 kilojoules per mole. Questions on that? You've already done this. This was in the lab. This was the last part of that lab where you got a whole bunch of pressures and a whole bunch of temperatures. You had to turn the pressures to ln of P, temperatures to 1 over T. Then you made a graph. You did the graph, you got a slope. Then you took that slope and multiplied it by -R, and you determined the delta H vap from that. Again, the reason we are doing this, we can't measure the heat of vaporization. We can't measure it. We can't measure it easily, but we can measure temperature. We can measure temperature easily, and we can measure pressure easily. So we've got two things we can easily measure. We make a graph, we can determine the third thing. That's why we're doing this. Now, if I take two pressures and two temperatures, I can take my Clausius-Clappeyon equation and I can subtract one of them from the other. And when I subtract one of them from the other, I create the Clausius-Clappeyon two-point form. And that one is the ln of P2 over P1 is equal to negative delta H vape over R times 1 over T2 minus 1 over T1. The point is, you got to make sure when you're one of the main ways you can screw this problem up is not associating the right pressure with the right temperature. You got to look at the problem, see which pressure is associated with which temperature. Okay? The temperature and pressures that are associated with each other, one goes on top, the other one goes in the first part of this 1 over T2 minus 1 over T1. The second one goes underneath, and the second one goes in the second position. You got to make sure you keep the same temperature associated with the same pressure. Note, all of these equations are mathematically equal. All of them are mathematically equal. They all work. What I want you to do tonight, decide which one you're going to use and stick with it. The only reason I'm showing you all three is that sometime you're going to come across a reference somewhere that is going to mention one of these other forms. And you're going to look at it and say, well, that's wrong. It's not wrong. It's just a different way of mathematically solving for it. So now that I've mentioned that, right now, I want you to just look at the middle one. Forget this one. Forget this one. Just look at the middle one, and that's the one I want you to use. Now, let's look at the equation. All right. If T2 goes up, if the temperature goes up, what happens to the pressure? Let's analyze the equation itself. If T2 is bigger than T1, what is the sign of this portion of the equation? Is the sign positive or is it negative? Okay, T2 is bigger than T1. If T2 is 3 and T1 is 2, I get 0.33 minus 0.5. Is that number positive or negative?
Negative.
It's negative. All right. So this portion of the equation is negative. I'm multiplying that by a negative. What does that mean? The whole right side of the equation. Is the whole right side going to be negative or is the whole right side going to be positive?
Positive. Right.
Okay. Now we got to think of logs. How do you get a positive number when you're taking the log of something? If you have a positive log, what does that mean about the number you're taking of log? Is it bigger than 1 or smaller than 1? Guys, I don't know is a perfectly good answer and it saves us a lot of time. If my value is positive and my ln is P2 over P1, if my value is positive, what does that say about my ln? Is this number going to be greater than 1, equal to 1, or less than 1?
Less.
Second guess, Joe.
It's greater.
In order for us to get a positive value for the log, the log has to be greater than 1. If the log is less than 1, ln of number of fractions are negative. ln of numbers greater than 1 are positive. ln of 1 is equal to 0. So if I have a positive number here, that means that my ln has to be greater than 1. The only way for that ln to be greater than 1 is if P2 is bigger than P1. Guys, this is how you analyze a question. This is a typical MCAT question involving chemistry. They will give you an equation like this and then give you the question. If temperature goes up, what happens to pressure? And you got to sit and analyze through the equation, just like we did, to figure out what happens. And it also makes common sense. If the temperature goes up, you have more energy getting more molecules into the air, so the pressure is going to go up. Problems involving 2-point Claussius Clappeyon. Benzene has a heat of vaporization of 30.72 kilojoules per mole and a boiling point of 80.1. At what temperature does benzene boil? When the external pressure is 445. Let's see, I've been given one pressure, but that pressure I gave involves a temperature I don't know. I've been given a temperature, but I haven't been given a pressure for that. Seems like I haven't given you enough information. What can you say about the pressure when you've reached the boiling point? If I have the pressure at the normal boiling point, if I have the substance at a temperature that is the normal boiling point, that is the boiling point at 1 atmosphere. So if I know what the normal boiling point is, I know the pressure associated with it is going to be 760. Now I'm going to plug it into the equation. I know that my temperature is going to be, remember, I got to change this to Kelvin. My temperature is going to be 81 plus 273. That's going to correspond with 760. My P1 was given in the problem of 445. So the P1 is going to go there. My heat of vaporization given in the problem. My R was also given in the problem, or my R is a constant of 8.31 joules. Now, is my heat of vaporization in joules, Joe?
My bad, keep being muted. Would you repeat again?
Is my heat of vaporization in joules?
It should be in kilo.
Yep, good. So my heat of vaporization is in kilojoules. My R, it's heat of vaporization always will be given in kilojoules. My R is in joules. So I either have to convert R to kilojoules, or I have to convert my heat of vaporization to joules. It's not going to matter. I either convert heat of vaporization to joules or my R value to kilojoules. It's not going to matter. So when I plug all that information in, I get 445 over 760 is equal to my heat of vaporization divided by my R value divided by 1,000 to get kilojoules times 1 over T2, because T2 is associated with 445. My 353 is associated with 760. I divide this by this, I get 0.586. So my ln of 0.586 is equal to 3,695 times 1 over T minus 0.00283. I do this log, I get a negative 5.34. That's equal to negative 3.695 times 10 to the third over T2 plus when I multiply this times this, I get 10.5. Subtract 10.5 from both sides, I get 15.8 is equal to 3,695. T2 is equal to 3694 divided by 15.8. My T2 is equal to 234. Now, there are a couple things that go wrong with solving these problems. First of which, again, you got to associate the right pressure with the right temperature. Second thing, you got to make sure that your heat of vaporization and your R values are either both in kilojoules or both in joules. Now, the third thing is going to be a problem when you are solving for the pressure rather than the temperature. And I'm going to get out of here for a second. That's not what I wanted. Now, if I was going to ask you a question, that's not what I want. And show. Okay, I need home. I need new slide. Okay. If I was going to do a problem where I didn't know the pressure, but I knew it boiled at, say, 310 Kelvin. My heat of vaporization is 36,000 joules divided by 8.314 times 1 over, what do we want to say? Give me a number from 1 to 10. Okay. Minus 1 over now, when I'm solving this, again, I'm doing this by the seat of my pants, guys, so something might end up being a little bit funky here. All right. Oh, crap. This is not going to give a very good answer, but all right. When you get to this stage, in order to get rid of the ln, I have to raise both sides to e to that power. So I get e raised ln x divided by 760 is equal to e to the negative 0.996. All right. The key here is, you notice I did not multiply the 0.996 by 760 and then raise it to e's power. What you have to do is you have to raise the right hand e to that power, and you have to raise this to this power. This reduces then to x divided by 760 is equal to and this is going to be a silly thing. Sorry. Why is this not doing this? That's better. That's how you have to solve that particular problem. Now, any questions about Claussius Clappeyon? Do I still have people out there? Oh, I have 5 people. Any questions about Claussius Clappeyon? Guys, I have a set of problems, a PowerPoint that I'll make sure is in my courses before I leave tonight. Look at those problems. They're solved step by step. Look at those problems before Thursday, okay? All right, last thing I need to discuss. I'm not going to get to phase diagrams, but that's okay. It's not in the test anyway. All right. When all the molecules have the necessary thermal energy to evaporate, we are at the boiling point. So basically, when we're at the boiling point, vapor pressure equals the external pressure. Boiling point is reached. So we're involved. We're involved with the energies of phase changes. Yes, we're dealing with thermodynamics, but the great news is there aren't any more formulas to memorize. We're going to use formulas you are already familiar with. We're going to deal with the energies of phase changes. Now, I'm going to take you through the journey of ice going from -25 degrees Celsius to the point where I have steam at 125 degrees Celsius. There are sloping regions and there are flat regions in this curve. You notice I have the flat regions. Am I increasing the temperature? When I have the flat regions, is any of the temperature going up? I'm putting more heat in, but the temperature is not going up. Why? Earth to fandom. Mr. P's fans, where you at? Jessica? Joe? I'm adding more energy in here, aren't I? I'm going from 15 kilojoules per mole all the way to 55, but the temperature isn't increasing. Why? Joe, Jessica, are you out there yet? Min. Come on. Where are you at, guys? Ian, you out there? All right, guys, I want everybody to unmute now. Do you all go off to eat dinner early? Jessica,
Yes.
did you go off to eat?
No. I just don't know the answer.
That's fine. Tell me so I'm not sitting here. All right. What's happening, Jessica, in the flat areas? I'm going from a solid to a gas. So all the energy I'm adding at this point, all that energy is going into breaking the intermolecular forces which cause the substance to be a solid. I'm breaking those intermolecular forces. So now they are now liquid. So all that energy goes into breaking that intermolecular force, which is causing my substance to be a solid. Now we're breaking all those intermolecular forces. All the energy is going into that. So the temperature can't increase. Then, once I have broken all of those intermolecular forces, I'm free as a liquid to increase the temperature. And I'm increasing my temperature until I reach the boiling point. Once I reach the boiling point, I got to take it from a liquid to a gas. So all the energy is getting put in to making all the liquid molecules into gaseous molecules. Then once I have changed all the liquid molecules to gas, I'm free to increase my temperature again. So when I'm changing it from a solid to a liquid or from a liquid to a gas, I am not increasing the temperature. I'm using two formulas. When I am within the same state, when I am taking ice from minus 25 to the melting point, I am increasing the temperature. I have to increase the temperature to get it to the point where I can then change the ice into water. The formula I use is the same one you used for the calorimetry problems. My energy Q is equal to the mass of water times my specific heat. the specific heat of ice is different than the specific heat of water, which is different from the specific heat of steam. The specific heat is dependent upon the state of my matter. So if I'm taking it from solid up to the melting point, I'm going to use my specific heat of ice. And I'm going to multiply that by my temperature change. So that's what's happening in this phase. Now, when I go from a solid to a liquid, I have to use another equation. And that equation is my energy is equal to my moles of my substance times, if I'm going from a solid to a liquid, I have to use the heat of fusion. So my energy is equal to moles times my heat of fusion. When I'm going from my liquid at the melting point up to the boiling point, again, that's involving a change in temperature. Again, I use the Q is equal to M times the specific heat times the temperature change. My energy is equal to the mass of my substance times the specific heat as a liquid times the change in temperature. Then when I go from a liquid to a gas, again, it's the flat portion of the curve. My energy is equal to moles. This time though, since I'm going from a liquid to a gas, I'm going to use my heat of vaporization. Then last, I'm going from the boiling point to the liquid at a higher temperature. Once again, I'm going to use my energy is equal to my mass times my specific heat of the gas times my change in temperatures. So bottom line, if it's a line that is slanted lines, you use the MC delta T formula. If it's a flat line, you use the N times delta H formula. Each specific heat is going to be different for different stages. The heat of fusion is going to be different from the heat of vaporization. Another thing you need to count on. If I am going in, I don't want that. If I'm going in, stop that. If I'm going in this direction, if I'm going from ice to a gas, my final temperature is always going to be greater than my initial temperature. Does that make sense, guys? If I'm going from a solid to a gas, isn't my temperature increasing? If my temperature is increasing, then my final temperature is greater than my initial temperature. Fair enough?
Yes.
Okay, so that one's easy. As I'm going in this direction, my slanted curves are all going to be positive numbers. It's all going to be endothermic. Now, Jessica, now that I have you real quick, does it take energy to turn ice into water?
Yes.
So is that an endothermic process or is it an exothermic process?
Endo.
What's the sign of endothermic processes?
Mm.
You see me?
Plus positive.
Plus. Endothermic or plus. So when I'm dealing with the straight lines, if I'm going from a gas, excuse me, if I'm going from a solid to a gas, the straight lines are going to be positive numbers. If I'm going in the other direction, the straight lines are going to be exothermic, because if I'm going from a gas to a liquid, in order to do that, I have to give up energy. So going in this direction, all your numbers have to be negative. Going in this direction, they have to be positive. So let's get one problem. I'm going to deal with one problem, and then we're going to be done for the semester, guys. I know I'm going a little bit over. I'm sorry, but this needs to be done. All right. How much heat does it take to raise the temperature of 25 grams of water from 55 C to steam at 150 Celsius? When you're doing a problem, what I want you to do first is draw it. So I'm going from 55 slanted line, straight line horizontal, slanted line. I'm going from 55 to 150, and it's water. What's water boil at? Come on, what's water boil at? Okay, we're going to deal with this. Water is going to boil at 100 degrees. You should know that water boils at 100 degrees. So to solve this portion, I'm going to do Q is equal to MC of my final temperature is going to be 100. My initial temperature is going to be 55. To do this part, my Q is going to be equal to N times delta H vaporization. This is going to be a positive number because I'm going from a liquid to a gas. That process is endothermic. So I'm going to put a positive sign in front of it. Then to go from 100 to 150, so to dealing with this portion, my Q is going to be equal to my mass times my specific heat times 150 minus 100. Anybody have any problems with this? All right, I'm going to go back to the slideshow because those calculations are already done. So the question is, how much heat does it take to raise the temperature of 25 grams of water from 55 C to steam at 150? Strategy-wise, you have to solve this as 3 problems. Then, once you've solved the 3 problems, add up all the energies. You're going to raise the temperature of the water first from 55 to 100. Then you're going to take the water from liquid to steam. Then you're going to raise the temperature of the steam from 100 degrees to 150. Solving the first problem, I got 25 degrees. My specific heat of water is 4.18. My temperature, my final temperature is 100 minus my initial temperature of 55. I multiply that all out. I get 4703 joules. Now, this is important. I want you to change everything into kilojoules. That means if I have 4,703 joules, I'm going to multiply that by 1 kilojoule over 1,000. I'm going to divide that by 1,000. I get positive 4.703 kilojoules. So I know how much energy it took to go from 55 to 100 degrees. Now I'm going to figure out how much energy it took to go from a liquid to a gas. This equation, my Q is going to be equal to my number of moles times my heat of vaporization. I had 25 grams. My molecular weight is 18.02. This means I have 1.39 moles. 1.39 moles times 40.5 kilojoules per mole gives me 56.2 kilojoules. I'm on to my third step. Again, I am going from a liquid to a gas, so this means this number is going to be positive. Okay, my Q. Again, I'm doing the third step, which is taking the gas at 100 degrees up to 150. Again, I'm going to use MC delta T, 25 grams. You notice I changed to specific heat. Steam has a different specific heat than water does. I'll take 25.0 times 2.01 joules per gram Celsius times my delta T. This ends up being 2,512. I turn it into kilojoules. That is 2.51. Last step, to get all three, all I do is add the energy of each one. That gives me a total of 62.8 kilojoules. Questions, ladies and gentlemen? The last thing, the only thing I didn't get to in this chapter were phase diagrams. You are not responsible for that for the test. Questions, ladies and gentlemen, on anything?
Nope, I understand it.
Good enough. Guys, it has been a semester. It's been great. I really, really appreciate all of you lasting till the very end. I really appreciate that. Guys, you've been champs, pushing through this stuff. It's not easy. I understand it's not easy. You made it this far. Keep on pushing. You have 2 more tests and you're done. Give me your best effort, okay? It has been an honor, guys. It's been an honor being here, trying to guide you through the myriad mazes of chemistry. I really sincerely wish you all the luck in the world, but you're not going to need it because you all are capable.
Thank you, Professor.
Anything you need from me, guys, you have my number. You get involved in Chem 2, you don't know what something is, use the number. I'll be happy to help you at that point. Good luck
So wait,
to
is
you.
this the last? Is this
This
the
is
last
it.
Zoom call?
This
Oh,
is the
man.
last Zoom. You have a test on Thursday, and next week you have from Monday until Wednesday to take your final.
Okay.
Any other questions, guys?
No.
Jessica, you got to
Oh.
say goodbye.
I was waiting. Thank you, Professor. Thank you for all your help.
Hey, it's been my pleasure, okay? It really
All
has.
right.
I've enjoyed every one of you, even the people that aren't here. I've enjoyed you. Men, at least men, give me one. Give me at least a goodbye, man.
I think Min had already left.
Ah, fair enough. Ian, you still there?
Yep, I am.
Good luck to you all, okay?
Thank you so
Thanks.
Take care.
Well,
Again, keep the number. If you need help in the future, don't hesitate to ask. All right?
Got it.
Take care.
Thanks, Professor. Bye.
Bye.
I have a question once everybody leaves. Okay, so for the test.
I'm sorry, one
on-
second. Ian, is this something
you-
personal? Do I need to stop recording?
No, I don't think so personally. It's
Okay.
it's on the test. So there's no practice exam, right, for this one?
If it's not out there, Ian, I didn't get a chance to make it.
Okay,
Uh,
I haven't looked yet.
Literally speaking, if it's not there, I didn't get a chance to make it. And my car broke down on the way to South Florida. So I had to deal with that all weekend. So again,
Well,
crap happens. I realize that. I'm sorry that if there's not a
no, you're fine. It's no big deal. I should be good on this exam without it. Is it going to be a lot? I don't really know how I'm wording this, but is there a lot of multiple choice or is it more work-based questions?
I think this is. I can't answer that until I look. Okay.
It's fine. No big deal.
If you don't mind, I don't mind looking.
Okay.
I don't mind looking, but I need to figure out where I am. Okay. I'll look at the final as well.
Thank you.
The final, I think, is all work-based problems, if I remember correctly.
Okay.
All right. First, first 20 questions, Ian.
Okay.
First 20 questions are multiple choice, true, false. So 20 times 4 is 80 points. Okay.
Oh, okay.
And there are 3 problems. 3 problems
Oh.
after that. And
Okay.
there is a 1 extra credit point, a 1 extra credit problem. Okay.
Alrighty.
So
And then I can do the lab exam tonight, right? It's already open.
it should be yes.
Okay.
All right. Now the final. And I'm fairly certain these are all going to be problems written out. They're all problems.
Okay.
All right.
Thank you.
No problem, man. You
Good
take
luck
care.
with your car. Thank you for this semester, Professor.
Oh, my car's already fixed. I just have to go down, drive down to South Florida to pick it up tomorrow.
Oh, okay. Well, have a good drive.
All right. You take care then.